Hey, hello everyone. Good morning. I hope you started a great day. Today, let's continue our discussion about the harmonic mitigation and filtering in our inverter-based kind of like systems. So far, we talked about the origin of the harmonics, why we have harmonics or those distortion. We learned how to quantify the distortion with a uh, parameter that we define named THD, total harmonic distortion, and we use the components, the values in Fourier series, use them in order to define the relative distortion of harmonics to the fundamental. Okay, and we normally represent THD as a percentage, kind of like uh, value. Then we move on to the okay, we know that we have harmonic, we know that we cannot get rid of them. Now, how we could control our system or like manage the situation in a way that we reduce the level of the distortion, get ourselves in a situation, the better situation as much as we can. Okay, so the first idea that we focused on previous session was okay, let's try to control the switching in inverters because we know the cause of those harmonics is the switching. So let's control the switching with different kind of like leverages that we have in hand on that control system in order to have a lower harmonic. We said, okay, by using a PWM in a way, like for example, having a triangular waveform as a carrier in the PWM, we already are able to eliminate the even harmonics, the even multiple of our fundamental. So that's something that we get when we choose the carriers as we chose in our previous session. We talked about in the previous session, and we also learned because of the characteristics of the Fourier series of a square wave, using those technique, the PWM technique, already helped us to have lower amplitude of signals at higher frequency. So if the frequency goes higher and higher, increases in the spectrum that we have, the harmonics that we have, when we go in higher frequency, we have lower amplitude. So it's already giving us a better kind of like situation than just a random switching. Okay, so PWM is already gifting us with those characteristics, but that's not enough. You still need to make a better situation. So we learned that, okay, because we have some leverages like the switching frequency, okay, or the initial phase angle of the carrier and initial phase angle of our reference frequency and modulation index. These are the values that we could change in our control system by optimizing the combination of those values. Okay, we can uh, suppress or mitigate harmonics. Okay, now we had two strategies. Either we could optimize it to minimize the total harmonic distortion so we don't target a specific frequency. Okay, we try to generally minimize the harmonics. Okay, or as we know that, okay, the harmonics are going to get lower and lower when the frequency goes higher and higher, one strategy would be let's target the lowest harmonics in perspective of the frequency. So let's target exactly the third component, the fifth component, and the seventh component, or like maybe 11th component, those low frequency harmonics that we have. So because we know already that the higher frequency has already like naturally has low amplitude. So let's get rid of these low frequency harmonic, okay? And when I say low frequencies, it's still higher than fundamental, but it's lower in a spectrum, okay? Relatively. So we could have a better situation because those uh, frequencies in the beginning of the spectrum of the harmonics have more kind of like uh, contribution on making the THD. So if we target them, it's again a good strategy to lower the overall THD. So that was the two kind of like suggestions that we learned since the PWM is kind of like a digital kind of like algorithm is basically how to manage that is optimization system. We have multiple variables. We have several equation. Analytically, we cannot solve it because we have multiple harmonics. Okay, so we have more equation than we have variable. Okay, so we can solve it analytically, but numerically, it's an optimization problem, and it's going to be fixed very easily by a simple, like even simplest optimization method could help to get to the reduce the harmonic situation. Any question? This is the what we talked in previous session. Any question so far about those concept? No? No. Let's move on and continue to our discussion. Yes, we already like talked about the optimization of the switching patterns. We have leverages. We could use those leverages to optimize our switching. Another way to control the harmonics, which is still a software kind of like solution, is to use more advanced control techniques. We know that the foundation of our switching technique is PWM, or in our case, we want a sinusoidal as our desired waveform is a sinusoidal PWM, which is SPWM. Okay, so this is our baseline, but there are some advanced technique, mostly consider kind of like the newest techniques are using machine learning or AI, okay, or kind of like a more advanced technique rather than like a feedback loops, like a simple PI or like a simple PID loops filter. They use more advanced kind of like techniques in order to optimize that those variables in SPWM. So another way is that. Now, I mark that topic, the advanced control techniques of SPWM with those two fire, okay? Because if you remember at the beginning of our course, I said using an innovation would gives you a huge advantage grade-wise and learning-wise, okay? This topic is one of the, I could say, most popular and easiest topic that you could have innovation because you're using advanced control technique that probably used in other areas, other field of engineering. Try to combine them with SPWM and see now if it's make it better. We have a better optimization, or we have less computational work. We have simpler kind of like system or not. So this topic is a very good field if you wanted to like take advantage of that innovation part in our syllabus. Are we good? So you could use that very much. Now, we already said that there is one of the advantage of the advanced control system is to incorporate artificial intelligence and real-time harmonic reduction. As I mentioned in previous session, these artificial intelligence and real time are still in research kind of like level. It's not done in a commercialized kind of like scale. Okay, so this topic is also could be one of the topics that you might want to like get deeper in that. Okay, because it's a very good kind of like area of innovation. It's still not mature enough. Any questions so far before I move on to the next concept? Are we good? Okay. So far, what we talked about the harmonic mitigation, harmonic suppression is the software techniques. Mostly includes how to optimize our switching techniques to cancel out the distortions. That was our initial plan. Now, as I mentioned, even if we use the optimization and do everything right in switching, because we use switching, it is going to be harmonics introduced to our system. So we need another layer of defense in our system against harmonic. Then comes in the hardware solutions. Okay, or like one of the most typical hardware solution to eliminate the harmonics is kind of like a very easy answer. Okay, if someone asks you, okay, how do we want to like eliminate a frequency? The first thing comes to mind is, okay, let's have a filter. Okay, now you know already that there are several type of filter. We could have like active filters. We could have that there's a variety of design in active filters. Okay, they have more expensive kind of like configuration. They have more computationally expensive algorithm for control. And another category is passive filter, which there is no control. We design it based on our desired frequency and our system and let them do the work. Okay, so cost-wise, passive filter are better than active filter. But when we go into the design of the passive filter, we are going to see the limitation of the passive filter. If it's important for us, we have to move on to the active. If not, passive is the answer. Normally in power system, they in a low, like medium level system, like MV grid or like a LV grid, low voltage grid or MV grid, they do not go to the active system because it doesn't worse the cost. Okay, but in a higher kind of like perspective, like in transmission line, when the amplitude of the current and voltages are very high, then relative wise, we said THD is a relative to the main component. Then relative wise, harmonics play a sensible kind of like role. So we need to have a more advanced way to deal with them. So on that level, we have a certain compensation, the active filter, like normally they call it like either like a harmonic compensation or statcom. Those they use the statcom also as like a compensation of the harmonics, or like a simple active filter that you learn in probably ELAB or analog design in electronic. Okay, so any question so far? That was the introduction of the hardware solution. I want to move forward to the actual hardware solution that we want to have. In hardware solution, we would have two types of filter that we normally use or design in order to deal with the harmonics left out of our after our optimization. So we done our optimization. This is the best we can do. Still we have harmonic. Now we want to deal with it. Okay. Two types is LC filters or LCL filters. Okay, more general kind of like types. Now, the LC filters, as you might know, I don't know if you are work with the LC filter or you've seen LC filter or not. Did you have any course on the filters or filter design? Which course?
DSF. DSF.
DSF? Oh, digital signal processing.
These are from two. Yeah.
Yeah, we talked about that. If you have ELAB, we talked about the filters. We have one big specifically for filters. Okay, but yeah, but regardless of that, we are going to talk about the more practical way of filtering. I already uploaded a file that explains the theoretical parts of the filter, the background of filters. Okay, you could search by yourself. There's tons of other references on internet. This is not a new technique. Filters are a mature, passive filters especially are a mature technology, so you can find everything you want in the internet. In YouTube, you might find a video that exactly tells you what to do step by step to design a filter. Okay, but we wanted to like go over them in order to like get familiar. Now, the first type was LC filter. LC filter considered as a second order filter. Why second order? Anyone knows how you count the order of a filter? Why LC is second order? When we talk about the component, the passive component, we have RLC. The inductor and the capacitance, okay, they both are differential integral component. So if you wanted to like calculate the behavior of them or model the behavior of them, either like for a component for inductor, you already know is voltage is equal to L di dt, so it's a differential, okay? And C is an integral component. So voltage is 1 over C integral of current dt. Okay, now you have both of them. If you want to come up with one equation to describe all of them, you can't have both integral and differential in the same equation. So you have to differentiate once more to have only differential, meaning now you have a second order differential for inductance and a simple equation for capacitance. Makes sense? So this is why we call this a second order filter, because the equation that models the behavior of LC filter is a second order differential equation. And one way to know kind of like have a better kind of like situation is that we have two types of differential integral component in it. So it's second, like an RL filter, it has resistance, is not differential integral component, and it has one inductor in RL filters. Okay, so because we have only one component that is a differential equation, we have first order filter. Okay, we have LC, we have two type of component with a differential integral equation that describe their model. So we have second order. Are we good? No. There are different type of LC filter. I put the names and the output kind of like performance of those filters on the slide. You could search on them. They are different based on the configuration. LC filter doesn't mean that you have one capacitor and one inductor. You could have a circuit, more complicated circuit, but it is eventually could be described with LC filter. You know, this is the equivalent, simplified version of that complicated system. Okay, there are different types. You could search on them and learn about them, but an LC filter, how it works, how it filter out harmonics or several harmonics. Okay, anyone knows what concept the L and C use to let, like this is a low pass, let go of a certain harmonics, but down or kind of like mitigate other harmonics. So this circuit would let go of some of the frequency, let them pass through with minimum damp or minimum effect. And some of the frequencies, they would damp significantly.
Would that be like a bandpass filter? Or
We are only talking about the low pass filter. So bandpass filter are more complicated structure, okay? And instead of like you see here that some of the frequencies are passed through, and after a certain frequency, the other frequencies are damped. This is how the filter, the LC filter works. This is low pass LC filter. Okay. My question is, what is the characteristics? What is the kind of like the characteristics that help LC filter to do that? Yeah, go on. The concept of the impedance in L and C. We know that the impedance of L is J omega L, correct? And the impedance of C is minus J over omega C. In low frequency, okay, means Z of L is low, but Z of C is high because impedance of L has a direct relation with frequency. Impedance of C has a reverse relation with frequency. If we have low frequency, C is showing high impedance, L showing low impedance relatively. Okay?
So it's basically channeling the high frequencies and then grounding them, right?
Yes. So now, in high frequency, it's reverse. In high frequency, ZL is going to be a high value, and Z of C is going to be a low value. Like if frequency goes to infinity, you could see that the capacitor becomes short circuit and the inductor becomes open circuit. See? And is in zero, you already know in DC. In zero, you consider inductor as a short circuit and capacitor as open circuit. That's the impedance kind of like configuration. Is that clear? Now, imagine there is a current moving in. That current has several components. The fundamental, the third harmonic, the fifth harmonic, all the way to like the infinity harmonic. As we said in AC circuit analysis, when we want to like analyze an AC circuit, we do one frequency at a time. Okay? And then use superposition to see what's going to happen. So when this frequency is coming into that filter, the fundamental frequency, this is the lowest frequency that we have. The impedance that it sees in inductor's branch is lower than the impedance relatively than it sees in capacitor. So based on the current division rule, remember that? KCL, current division rule. The current wanted to go through the lowest resistance. So the lowest impedance, the current, majority of the current will flow through the lowest impedance. So the majority of the current for the fundamental flows through L to our grid. Okay, a little bit of it flows to C. It's not zero, but it's very low, relatively. Now, I'm going to increase the frequency to the third, harmonics. What's going to happen? The impedance of the L rises, the impedance of the C falls. So now the harmonics, the third harmonics sees lower impedance to the C branch than L branch. Okay, so it prefer to go toward the C branch. So it gets to the ground. A little bit of it pass through the L. Now, fifth harmonic. The impedance of L is higher, even higher than the third one. The impedance of the C is even lower than the third one. So the fifth harmonic prefer much better to go to the C branch than L branch. Get grounded. And it goes all the way to infinity. When we're talking about the infinity, the frequency of infinity, it fully goes through the C branch because it's a short circuit rather than an open circuit in L branch. Are we good? So this way, the lower frequency prefer the passing through L, going toward our circuit, our grid, and the higher frequency prefer the C branch, so they pass to the ground. This way, we cancel out higher frequency and let go of lower frequency to the grid. Is that clear? This is the mechanism of a LC filter. Now, before I go, this frequency that divide the pass-through and cutting off the mitigation. There is a frequency that divides these two bands. Lower a certain frequency, we'll let go of the harmonics with minimum down. Higher than that frequency, we mitigate them. We ground the frequency with a high damping factor. Okay, that frequency we call it cutoff frequency, or sometimes they call it resonance frequency, and it's equal. You could calculate it based on the value of L and C. It's 1 over 2 pi square root of LC. So for example, if you wanted to design a filter for a 60 hertz, you want to make sure that the 60 hertz here pass with 60 hertz is in this area, so we don't damp it. Next harmonic for power grid, we said the next harmonic is the third harmonic, right? So it's 180. We want to make sure that 180 happens in this area. So this cutoff frequency should be somewhere between 60 and 180. Normally they put it closer than 60 than 180. So it's around like 100 frequency, 100 hertz. So it's practically. So they make sure that all the harmonics fell over the cutoff frequency, so they are damped significantly. But our fundamental, we let it go with minimum damp. This is ideal. This that you see, the gain factor is 1, so mean is no damp. This is ideal case. Normally there is a little bit of damp because you never get an open circuit in low frequency for C. There is still a little bit of current passing through the C. That is the damp factor. Okay. Now, any questions about these? Now, I want to add a parenthesis in a filter design. Okay, when you design a filter, the low pass filter especially, okay, this is the ideal case, or like the graph that you see as a gain of your filter. Okay, what they don't tell you that this graph is based on lumped model. Anyone knows what lumped model is? Lumped model, we have distribution model and lump model. Lump model is when you define a certain environment with one L and one C. This is a physical material. There is a physical material that you show the characteristic of that physical material with one inductance. So it's you basically make it a compact parameter. It could be like a huge cable, okay? But you show it with one compact L. This is lumped kind of like situation. Lumped, Lumpd.
Oh, okay.
Yeah, lumped. There's an E also. Yeah. Lumped model against distributed model. Okay. Another way is a distributed model. So you don't represent an environment with one parameter or one component. Is a network of several components. That's distribution model. Okay, so this is the difference. This formula is based on lump model. Lump model work when you are working in an area of the frequency when the wavelength of your signal the wavelength of your signal, which is 1 over f, okay, the wavelength of your signal, okay, is uh, not very lower than your actual physical dimension. If you have, for example, like a regular kind of like inductor, for example, is 1 centimeter per 1 centimeter, the physical dimension of that inductor. Okay. If you put in like a gigahertz signal or a megahertz signal, because the wavelength of the megahertz or gigahertz are much shorter than 1 centimeter, okay, then law model don't work. KCL and KVL don't work. Ohm law, somehow you have a kind of like amendment kind of thing to Ohm law. Okay. Why? Because when that condition happened, beside conducting energy, you would have radiating energy. Concept of antenna. Antenna works with that concept. You have a dimension that is comparable, okay, is much larger than the wavelength. Now you have radiation. This is the base of the antenna. Okay, so if you have a radiation, that means when I have a certain L or certain C, I don't change dimension. This is, I put it there. You know, I saw the inductor in my circuit. Now, when the frequency goes higher and higher, at a certain frequency, okay, now I see radiation. Okay, now the path that energy has is not just this C and this L. There is another pass through air. Okay. Normally they show it with a kind of like a air gap capacitance. If you go through the communication circuits and like microwave signals, like microwave analysis, they show it with a capacitance, which represent the air gap. Okay, conduction of the air. Okay. Then at the high frequency, this gain starts rising because now we have another capacitor that short circuits this L, parallel to that L in high frequency. Makes sense? So this is a practical kind of point. When you design a filter, pay attention to that. Ideally, low pass filter would cut off all the frequency after the cutoff frequency. Okay. But practically, after a certain frequency, when you go higher than a certain frequency, there is going to be another capacitor shaping in the air gap parallel to inductance. So it would short circuit your filter and let go of the high frequency through to this out. Is that clear what I'm telling you? So you have, when you design that, you have to make sure that you consider this practical kind of like situation.
A lot of filter circuits on PCB boards, they have multiple layers, because they don't.
This is not that you could avoid any filter.
No,
No, that's the reason that they put cascading filter is because to make filters cheaper, layer and layer.
like there are some PCBs that are 4 layers, that it's 2 layer, and it's usually the ones that have the radio on. I did some research.
Oh, okay, yeah. Okay. You mean PCB wise? PCB wise, yes, but still you have your conductor, you have your inductor. The inductor you cannot do that layer by layer. Yeah. So this is the kind of like the LC filter and kind of like the practical point of how to define the LC filter. The next part, the next type of the filter that we could have is LCL. Now we have 2L, 1C. You might see that I have an R. We are going to talk about why this R is there, okay, later on. But LCL filter is another type of filter. LC filter is more common because it's cheaper and it's basically do what we want in power. Okay, so normally we don't have to go toward the LCL, but that's one type that in a special kind of like application they might use. Okay, same concept is just try to use the matching impedance of L of the two L in order to increase the higher power transfer. Make sense? Do you know the matching impedance concept?
Yeah.
Anyone has a question about matching impedance? So basically the same concept, but with a more kind of like damp. It's because of the matching impedance, it gives you more ratio on damping higher frequency. Okay? Now, there is one thing that you have to be careful when you have LCL, and it's the resonant frequency, the natural frequency of LCL. Okay? Beside the cutoff frequency, you have a resonance frequency, which is, you could calculate it with the same, is 1 over 2 pi, the square root of the equivalent of the parallel L's times C. Okay? In the resonancy, as you know, it's basically, I assume you know the concept of resonancy. Okay? Instead of damping, it start adding gain to those components. So the harmonics that happen in a resonancy, the filter do not damp, but it tries to like actually amplify those frequencies. So you have to make sure that this resonance frequency would not happen in a critical point that you have a harmonic. This is one way, this is one of the threats of LCL factor. Concept is the same as LC, but this is one of the big differences between the LCL and LC filters. Now, in order to control this resonancy, okay, beside making sure that it doesn't happen in like near your harmonics, okay, you could add that resistor that I told you into your circuit. Normally resistor is series in, you could see that here, is in series with the capacitor. Okay, there are several kind of like configuration that you could have with LCL. That resistor would create a damping factor in the resonance part, which take care of that negative effect of amplifying those frequency in the resonance. It's basically that R create a damping factor, adding a damping factor to that near that resonancy. Any question? Are we good? Now, the design of a filter, as we already talked about, that is a kind of a trade. Okay, we know that, okay, we could have a very complicated circuit, or we could use like a huge inductor or capacitor in order to like make sure a very sharp cutoff frequency. Okay, but that means we have to spend more cost. So it's kind of like a trade-off between the cost and performance of the filter that you have to optimize and balance based on your kind of like application. One point that is very, very important in designing a filter is impedance matching. You are creating an impedance between your source. This is your source. This is your filter. And this is your grid, which is the load. You transfer energy through this impedance. This is an impedance. Is LC or LCL, correct? If you remember the matching impedance, okay, you know there is, I think it was covered in circuit 1, that when you want to like transfer maximum amount possible of energy through your line, your impedance, your transmission line has to have a certain, like to match the impedance of the load. If your Z of F match the Z of G, you are able to transfer maximum possible amount of energy through ZF to the grid. Do you remember that concept?
Yeah.
Are we good on that? Now, anyway, that any change in this matching would result on lower power transfer, which is one of the effect of impedance that you have to like take into consideration. When you design the impedance, you have to consider what is gonna be your future load. So you have to match that impedance. You can't exactly match it because the load is changing, okay? But you have a range, probability-wise. You can say, okay, it's mostly this range, so I'm gonna stick to that range. Okay? Now, what happens if they are not matched? Why there is a lower power transfer when these two impedances are unmatched? Reflection happens. It's a wave going through one media to another media. Like when you have a beam of light going through air and then enters a water. It has a bending, it has a reflecting effect. So when the energy with whatever frequency tries to exit the ZF and enter the ZG, if there is a difference impedance between them, some of them go through, a part of them would reflect back. Okay, it's a wave propagation kind of like concept. So, but if you match these two impedance, the wave would not see any difference, so it completely pass through. Make sense? Now, there are certain standards for harmonic reduction. As I mentioned before, we said like we wanted to like mitigate our harmonics, but we know that we cannot make it zero. We already know that. That's not possible. Okay? There is a threshold. There is a standard defined for that. That you have to follow the standard if you want to like connect your inverters to the system. I recommend you to go through these two standards and see how industry or how the regulators watch the problem of harmonics. They define a certain aspect that any design should comply with those rules. Okay, so this is kind of like very important. As an engineer, try to familiarize yourself with those standards. Anything you do, if you do not follow standards, is worthless. Okay? Any question? We already talked about that. Not important. Let's go to some practical LC filter design concept. Now, when you wanted to design your filter, first thing you do is to define the parameters that are important in your system and you want to work on them. First parameter, operating frequency, your fundamental frequency. You have to define that because you want to like keep it untouched by filter. Okay. Next, harmonic spectrum. What kind of frequency you have in your harmonic. For example, as the example that I made previously, I said like in a power system, when you have like a PWM with a square wave, the next frequency, ideally, the next frequency after first component, fundamental component, is the third component. Okay, so basically, you know that the harmonic spectrum ideally starts from 180 and goes up. Practically, it's not okay. Practically, we don't have ideal case. We have inner harmonics, okay, and some reflections of something happening between the 60 and 180, okay, and even below 60. Okay, there are something happening, but ideally, harmonics spectrum starts from 180. That gives you a good idea of where the cutoff frequency should be designed. Make sense? And if you have a maximum amount, for example, because we said the amplitude of the frequency as frequency increase will decrease, okay, when you follow those in decrease, okay, you basically at a certain level that those standards define that level. At a certain level, you let go of the other frequency. It doesn't matter. You neglect them. Okay. Now, I said practically filters do not mitigate very high frequency because of that parallel C, that radiation factor that comes into play. If the spectrum of your frequency ends before that effect, that makes your life much easier. You don't need to worry about that radiation anymore. But even if that happened and these are passing through your filter through radiation, those harmonics, the standards already draw the line before them, so we don't need to worry about them. They are accepted by the industry or the regulations. Make sure. Does that make sense? Are we good? So, harmonic spectrum. And we already also mentioned the load impedance. The matching impedance that we have. We have to have an idea of, okay, what kind of load we are gonna get attached to, what range of the load we have. So we try to match that load, match that impedance in our filter. Are we good? It's never gonna be exactly matched. That goes for sure in a conventional way, but we have to consider that. If you have a very high impedance filter, when your load is normally low impedance, you are gonna see a terrible kind of like energy transfer, or vice versa. It's the same, Now, I put another signal here because this is one of the aspects that normally people do not pay attention to and do not work on it. It's a good idea if you have any kind of like innovation or you come up with an idea that you could dynamically change your impedance to match the load. So you would create a dynamic filter still with passive component. Okay. Think about how we could do that. Okay. And based on that, we could introduce a new technology as a dynamic passive filter that matches the impedance. So make sure everything is the energy transfer is in the maximum level or near the maximum level. Makes sense? This is a very good idea. And I'm not gonna give you. I wanted to give you a hint, but I don't because I want you to be creative if you want to like work on this area. So this is also one of the areas that innovation could kick in. Okay. After you decide what are the main parameters of your design should be, now it's time to choose the component. For example, in a second filter, you have one inductor, one capacitor. You have to choose capacitor based on your system definition. So, for example, if you want to choose an inductor, you wanted to make sure that it would not get saturated, okay, and it can handle the amount of current that you're supposed to provide in the output. Make sense? These are kind of like a practical trick, practical tips that you wanted to like have in mind. So you want to choose the inductor that would not get saturated in your normal working. Very good. So, and it has a low resistance because you know that you have an inductor. In practice, the inductor is a conductor wrapped around a certain core. Any conductor has a resistance, so it's not just an L. There is an R in it. You want to make sure you choose the inductor when in a way that it minimizes the resistance, so you don't have much of a power loss in your inductor. Because your inductor is when your load current, that 60 hertz, pass through. So your majority of the energy pass through that conductor. If it has a high resistance, that means very high loss. Make sense? Are we good? Now, for capacitor, it has to tolerate the voltage that you are working in. It's not like capacitor can work in any voltage. That's in theory. In practice, if you over voltage a capacitor like one, I think that the if I don't make a mistake, the standard for testing a capacitor is 1.4. It has to of the nominal voltage. It has to tolerate that amount in a steady state and 1.7 for transient, for short time of the nominal voltage. Okay, so kind of like that's why I'm saying that standard is important. Sorry. Thank you. So that's why I'm saying that the standard is important because you see, I'm having these numbers from the standards for capacitors. Okay, and I tested capacitor banks. Some of the capacitor like I tested, they would explode in that voltage. Just like that, like huge explosion. Okay, so you have to make sure that the component matches your nominal voltage, can withstand the nominal voltage and the transient that you could imagine it would happen.
You said those are multiple of
Nominal voltage. Like if you work in 110, okay, it's gonna be 1.4 times that. Now, there are other, like in short term, this transient is not nominal voltage, is nominal transient. Okay, like for example, you have to see in what situation you would have maximum voltage, transient voltage in your system. For example, in power system, in three-phase power system, two-phase, a fault of two-phase to ground, okay, two-phase to ground in a three-phase system would create the highest level of voltage in the third phase. Okay, you could search on that. This is kind of like based on practice. I'm giving you this information. So based on your system, you know what kind of like what is the highest risk, what is the voltage that the worst case scenario that your capacitor would be facing, could face, and you have to pick a capacitor that could withstand that terrible situation. Make sense? This is kind of like the practical tip in a designing. Okay.
and the paper that explained. that led to it is, I think it's a really good, like,
Yeah.
physical, like, actual example, because it talks about the differences and it shows the graphs and the phases and
I am gonna talk about the concept that like I gives you the idea of why what happened, why two-phase to the ground creates the highest transient voltage in a three-phase system. When we go to like after midterm, when we wanted to like analyze the transient analysis of the power system, when we integrate the IBR, I am gonna like explain why this is the worst case scenario and how you can yourself find out what are the other scenarios and kind of like decide which one is the worst and which one is the more has more threat to your design. Okay, we are going to talk about them, so don't worry about it. I just wanted to like give you examples. Okay, are we good? Now that we know what are the rating of our capacitor or like inductor is, now it's time for us to design that cutoff frequency. That was the threshold for passing and not passing the harmonics. We design our frequency, our cutoff frequency, and this is the next step. For example, I put one example of like for design. You calculate the resonant frequency or cutoff frequency. Okay, for example, for I think I have an example in here. I will probably the next slide. You simulate the behavior of your design, okay, and based on your simulation, you select your LNC. Now, why is the last option is the selecting LNC value? Because in your design, so far you're working in theory, but it doesn't happen that whatever L or C you come up from your theoretical design would be available in market. So you have to calibrate your design based on market. So you come up with the area or range of LNC, and then you find the calibrated value in the market, and you start testing it to see if it fits your description or not. It is your desired result or not. Same goes for LCL is not different because they are basically the same. Not important, not important. Let's see those. Oh, okay, here. I mentioned that 1/50 voltage rating. I already talked about them. Uh, let's go through the example. Like for example, if we wanted to like design an LC filter, okay, that targets like we wanted to like have a filter in a single phase inverter that targets the 1 kHz frequency. Okay, so we want to eliminate 1 kHz. Okay, we would choose our inductor. We already talked about that. We calculate the amount of capacitor that we need for that inductor based on the frequency. And we have our, it's a very simple example of how to calculate the LC filter based on your targeted frequency. This is for having a cutoff frequency at 1 kHz. So 1 kHz goes into FR, 2 pi. We are using the formula of F equal to 1/2 pi square root of LC. So we can find C based on our chosen L, or vice versa. Same goes for the LCL. We find our target frequency We have our rating power for impedance matching. Okay, we could choose our 2L. We calculate our C, and for damping resistor, we could use the formulas, the equation of LCL filter is the second order differential equation that describes the dynamic of the LCL filter to find the damping resistance that we need for our LCL filter. Okay, there are tons of videos and like DIY kind of like videos on internet. You could go through them for a specific kind of like examples or like how to step by step design a filter. This is a very mature kind of like uh, technology. These two are general consideration when you want to like component selection. You want to use high quality. You want to have heat sink because you would have a power loss. And in your PCB, you want to minimize your interference. What that interference happen? I think you already know about the EMI and like the factor of the EMI. So this is kind of like the PCB design factor. It's a general PCB design factor. Any question about filtering? No, are we good? Okay, that's it for today. And thank you very much. If you don't have any question, we could stop our session today and have a good rest of the day.